All right, it seems to be live. Make a check to make sure and such. All right, let's see. It sounds reasonable enough. I mean, the mic is a little bit iffy sometimes, this one, but it seems to work well enough. And so we'll pop open this and we'll find me somewhere here too. Where the hell is the me image? What do I do with that? I guess that's it there. Probably. Ah, yes, there I am. All right. Oh, I should have used my virtual physicist sign, but anyway, doesn't matter. Off color, but that doesn't matter either, probably. Orange, sort of interesting. Yeah, I really don't want to waste time fixing it. Okay, never mind. So I figure I'll do some conversating about. All right, so as I pointed out, there's a lot to physics in the sense of you got to combine things like charge and magnetism and electricity. And their charge is certainly related to electricity, sort of in between the two. And the fact that I'm arguing the same force, but the manifestation of it, the function is different in the sense that magnetism isn't something directly converted out of electricity. It's something electricity causes to the stuff the electricity goes through. It magnetizes it. And that creates the effect as if it was a normal magnet, just created by a different mechanism than a permanent magnet's mechanism. And so it gets a little complicated because it just seems like there's an obvious connection between you put electricity into an electromagnet and it turns into a magnet, and therefore the electricity is making the magnetism, and that's a mistake. There's lots of mistakes to make, and lots of them because of the way we're taught about what's taking place, and currents and arrows and moving fields, and so I might have said something in past videos that wasn't entirely correct. Conceptually, what I'm arguing is correct. I mean, the basic idea that the force is the pressure and the electrons are the mechanism by which, electrons are ping pong paddles. The force is that's trapped between them is either gravity or at a gravity frequency, nothing, or at the or electromagnetic radiation. It can be turned into electromagnetic radiation. You'd sort of argue that all light, all the photons that we recognize as energy, are in fact converted gravity. That is, they started as gravity and were turned into something called light. So a nuclear bomb, the power was created by gravity. That is, the pressure that made the atoms and shoved the energy into them was gravity. And the photons are how that gravity is going to be manifest when it's released as the pressure between the electrons. Now, I'd say that I'm like 95% sure that's correct. So I won't be recontextualizing that fundamental description of the difference between the force and the matter bits, and the fact that the electrons are the mechanism by which the force is increased or decreased based on the proximity of the electrons and that kind of thing, and that the electrons are creating the frequency that becomes the frequency of the radiation, and in the form now of light, and that magnetism is just that same force, just segregated for the type. That is, the electron force, and the proton has a similar force. The electron force and the proton force manifest completely differently because the electrons and the protons are in completely different arrangements. The electrons being on the outside, in a big circumference, and the protons being in a small circumference. And so it's probably enough of a preface. So in the last video, I sort of was talking about the way a coil works and how the magnetism is manifested because of the atoms moving, and that creates this idea of the electrons jumping. And I don't think the electrons actually do any of this jumping. I don't think there is any free electrons in thinking about it. But the only way the only electrons you involve in this electrical transfer are actually electrons that are attached to atoms. And if you do actually rip them off, that is, move them in some real way, you create ions, you create broken atoms. And there aren't just a bunch of free electrons to fix that. And yeah, and the electrons, the free electron would be by definition an electron not attached by pressure. So it sort of doesn't make any sense. And so what's really happening is the electrons are being, the relationship of the electron to the protons. Let's say this is electron, this is proton. It's their relationship to each other that's changing. So you could see that on a surface, this blue bits are out and the red bits are behind, or the red bits are out and the blue bits are behind. You can understand that if you had a bunch of that, then if you hit it from any not perfect straight across angle, you'd always hit a red. So if I had a bunch of red, blue in this arrangement, you'd know you couldn't miss the reds. No matter where you hit, you'd hit red. And if you had them this way, no matter where you hit, you're going to hit blue. And that's a better description of what happens on the surface of a magnet. So, and as I'm going to explain, that better illustrates what's happening. So in a sense, let's just go with the little dots to make it simple. We'll just say those are protons, and then there's going to be the electrons. So let's say I imposed a field coming into here from a magnet, and the magnet I was imposing, let's say, was electron end or north end facing the atoms. What's going to happen is that these blue bits are going to repel each other in the sense that they're going to bounce back and forth reflections, and they're going to push the blue bits behind the red bits. So the electrons are going to tend to be behind the protons instead of in front of the protons. And the red end is going to do this similar to the other end, okay, in the sense that it's going to force the blue bits to the surface, and it's going to send the red bits behind. Now, what angle exactly these things line up on, I'm not going to speculate that's important or critically important or something that I need to commit to at this point. But as you can obviously see, that this now does exactly what I was saying, that any force coming at any angle is going to see just blue, and any force coming this way is going to see just red. That is, and that's essentially the nature of what the magnet's doing. And in this process of pushing electrons forward or backward, you increase the pressure of these electrons. That is, they're compressed. So if I do force them in any one of these directions, this pressure between them is increased. They're pushed together. So you can sort of understand that if I took something, I guess, that was this shape, and I pulled it this way, it would pull this way. And if I pushed it the other way, if I pushed them this way, they would push into a clump. And the clump means that they're denser in that position than they were when they were in this position. That is, they're closer to each other. And that's the increase that we call voltage. So voltage isn't the movement of electrons, it's the consolidation of them. It's just taking and making their volume, the volume they exist in, the amount of space they exist in, smaller. So in a sense, when you bring the magnet in, the electrons are occupying a space, okay? Before you brought the magnet in, they were occupying space. They'll no longer be occupying because they got pushed in a direction. Not much, but a little bit. And a little bit's all you need to increase pressure. with two ping pong paddles, I can go from very little pressure, bong, 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 to very high pressure, bong, 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 just with not much movement. I'm doubling the pressure with just, every time I move these things incrementally, I'm increasing the pressure. So, so yeah, the electrons aren't, in my opinion, traveling anywhere. They're not doing anything except increasing pressure. All right, so now this relates to charge and let me use brown because the blue is a little weak. To electricity, in the sense that another thing I sort of had, I wasn't 100% in what I said in the past correct. I've always sort of implied that there is no positive and negative charge. There's just a place where you change the neutral, the middle, where there's a middle, a ground, a medium state of pressure, and then everything goes lower. So we could argue that every atom has external electrons, and those electrons are at a certain distance from the protons, and they're at a certain pressure between each other. So I would sort of argue that among atoms, there's kind of a standard in this outer thing. It doesn't really matter if there is or isn't. The idea would be is if they were to share an electron, that electron is really shared. It doesn't go anywhere. The two atoms just use the same electron. So, I should have done the protons in the middle on red first. I should have used blue for that, maybe. Okay, so this is the shared electron. And that's a better image of what atoms are doing. And when they're bouncing around with each other, they clearly are communicating. So when two substances are in contact, even when they're not blended in or melted together, they're still in contact in the sense that they're sharing pressure. And that's what we would call charge. Everything that connects to ground has to usually connect to ground through some kind of conductor, even if it's a weak conductor like the atmosphere. But it's usually in the ground. It's some salts or some other mechanisms. Like you pour salt into water and you can make electricity go between them and do electrolysis. So you just have to make the substance conductive. And conductive just means that all those atoms are in some way intimately connected in the sense that they're sharing pressure. So if one of them gets more pressure, more voltage between its electrons, the other ones are going to feel that pressure and increase or decrease their pressure until they all have a neutral pressure. So ground would be essentially a place that has a level of pressure where everything has the same tension in its electrons. Its electrons aren't bent. Its electrons aren't distorted or perverted in some way to cause extra pressure. So there's a balance in the pressure in those atoms, as long as they're not insulators. So if they're insulated, they can be on the ground, but still have a static charge that's different, because there's no way for the charge to feel the other atoms. They're not connected enough. There's enough of there's an insulation, meaning there's not a way to communicate the pressure of the electrons, no attachment. And by structure, some substances just don't communicate pressure, like glass, meaning you could pressurize one atom on the surface of the glass and it won't pressurize the rest of the atoms. It won't, if there was a high pressure atom over on this side of the glass and a low pressure atom on this side of the glass, they won't communicate with each other and balance into one kind of pressure. So it's just in the nature of the glass structure that movement in the electron based on, its vibration based on its pressure, somehow the vibrations don't transfer, even though the atoms are connected to each other. They're not connected in a way that allows that vibrational pressure to be transferred. So there's some geometry that in some ways allows things to bounce. Let's say I could bounce one electron and it doesn't affect any of the other electrons. So it can be a certain geometry that is more likely to be an insulator and geometries that are less likely to be insulators. And that's the difference between a conductor and an insulator, is the geometry of the atom. That is how much it shares vibration. So metals share vibration very easily, and things like glass share vibration very poorly. Okay. Okay, yeah. So charge would just be this state of where you create a level of pressure. Okay, so level of pressure that is neutral. So we can just use the typical ground symbol and visualize it as the idea that it's just a bunch of mixtures that turn into one charge, one level of charge, and that's the neutral. And then you can have materials out here in the world that can have more pressure. So they have, the electrons are more condensed. So we'll say condensed electrons, and they can be relaxed electrons. So you can have, as Ken Wheeler would say, compressions and rarefactions. So some substance might be in a compressed state, some substance might be in a rarefacted state. So this would be minus, and this would be plus. And the point is those states can be balanced, or there will be some effort by the pressurized element or the depressurized one, in a sense that it will communicate with any other substance that will allow it to communicate that pressure. So if there are, say, in an atmosphere, there's some chance that there'll be an atom that'll get close to this high pressure and it will get pressurized by the pressure, and another atom is communicating in the atmosphere. And so the atoms in the atmosphere are connected, okay, even though they're jiggling and they're separate. They're not made into compounds. They're not water molecules or this or that. They're oxygen and this is nitrogen. The point is they're close enough to each other, connected, that their vibrations are being shared. So the vibration, let's say, is indicating pressure, and the vibration is transferring that pressure to the other electrons. It's pushing on them. By pushing on them, it's compressing them, creating pressure, and it's not allowing them to relax. So if they can't relax and they stay pressurized, then that's a voltage. And so that pressurization will take place, these vibrations will take place, and they tend to vibrate more in this direction than it's allowed to relax in this direction, so to speak. And you can sort of get the idea that that would create a compression that moves through this field of stuff, and it's through specific atoms. And so you can sort of understand that if that pressure becomes a pathway to this object that's very low pressure, right? This one lacks a lot of compression. So the electrons are very relaxed. You can push on them a lot because they got a long way to go. The paddles are way far apart, so you can afford to push them halfway together, and it still won't even be that. So the one thing has the paddles this close. The thing over here has the paddles this far away. And what's going to happen is that the current, the pressure, is going to move through the atmosphere, through the atoms that are vibrating by compressing them. And it's going to be able to release that pressure. So the high pressure will go through the atmosphere, through atoms. It will get to a place where this low pressure is, and it will relax into it. It won't be fighting back anymore. It will go, the pressure will relax that electron completely, and all the others will cascade. And so it will be a place where the force can go because the electrons all get relaxed when they get there. So there's no fighting back. There's no pushing back. So you're pushing this way and you're not getting any push back. So you can just keep going this way. So the pressure that was in one of them will drain right into the other one. And that's the concept, and that's why electricity is so jittery. And it's also why it breaks off a bunch of electrons off of atoms and creates light, is because those are the ions being created there. Some of the electrons are getting jittered. They're getting jittered so much that, you know, they move out of space and they allow photons to escape. The pressure between the electron and the atom. So the atom has pressure that's holding the electrons together, and it releases some of that energy because it's being vibrated so much. And so it releases some of that pressure directly to your eyes. Now, if all of the energy got released, if all the pressure could get released that way, then all you'd get was light and very little electricity. And in some sense, that's what you're looking for when you're trying to make a light bulb or something. You're trying to create a pathway that ionizes the least possible. Ionizes the most possible, and does so without in a way that's restorative. So, like halogen, the pieces that fly off because of the heat bounce off the glass and fly back into the element. So it kind of restores what it broke to make the ions, to make the extra photons. And it rebuilds the photons again, then so it can make them again, and rebuilds them and makes them again. So it lasts longer and creates more light than heat. Well, it creates a lot of heat. More light, let's just say. More energy in the form of something we can see as frequency energy rather than energy traveling through the conductor. So it takes less energy through the conductor, and more of it's converted into energy in the form of electromagnetic radiation. So it's taking the electrical pressure and increasing the percentage of it that leaves at a frequency versus the percentage that vibrates all the way through to the weaker pressure side of the conductor. Yeah, so this sort of explains the difference between the two, but you can understand that. So the magnetism has to do with how the atoms are configured with each other, and the electricity has to do with how much pressure that configuration creates. And so that's the difference. One's a position difference, and one's a shape difference, you could argue. It's probably not the best way to say it, but it's just the difference between pressure and appearance or configuration. So how the paddles are configured is one thing, and how close they are is another thing. So the electrical part is how close the pedals are. The magnetic part is how they're arranged to each other. Because, you know, whether they're well, there's no perfect metaphor here or analogy. The real difference is proton versus electron. Are the electrons forward, or are the protons forward, or are the electrons forward? Which one is pointed towards the surface? Which one's more towards the surface? So that's all that's happening, really. When you bring two magnets together, all you're really doing is pushing. So if I have them both the same way, you know, north, north, south, south, and they're going to repel, all I'm doing is pushing the electrons behind the protons on these surfaces, and I'm pushing the protons behind the electrons on these surfaces. And now you have constant reflections and constant reflections, and vice versa. When you do the opposite, you bring this one's making the electrons forward, and this side's making the protons forward. So now they're very attractive. The electrons are attracted to the protons, blah, 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 blah. And again, they're not attracted. It's just the low pressure. The pressure leaks out, as explained in the other video. All right, so I'll do a little bit on that leaking out part just to really complete this picture. But I think I've made the point to be made is magnetism, especially electromagnetism at first, is a surface phenomenon in a sense. You know, it's about how many atoms are involved in the process, but all you're really doing is lining up atoms in a form where they are polarized in the sense that they go from they're all misshapen in the same direction, and that creates magnetic domains, you could argue. So they're all misshapen in the same direction, and that creates like say this was a little domain inside of a piece of ferrous material or steel or something, and there's other domains pointing in other directions. Well, this domain itself will do, this is red, black, red, black, red, black. You have to, think of these as little magnets, even though they're not two colors. And the point is when the force comes in mixed, as I've pointed out, this will behave like a magnet in the sense that it'll reflect the same force, and it will transmit the other force perpendicularly through the material. And that can lead to it just coming back out again, but we're not gonna, it would come back out as red, of course. But the idea is that it does transmit it, because it's going to be, obviously the electrons aren't going to be, so say if I did distort an atom, you can sort of understand that the electron and the proton, if something is perpendicularly moved, you could argue, like, let's say this perpendicular direction is this way. I should have had it hit the brown thing. Well, it doesn't, you'll get the point. Point is, perpendicular won't be where this is located, it'll be this way. And so it'll always just keep hitting reds instead of hitting, so it just creates more proton pressure instead of instead of being reflected back. But anyway, the point of the magnet is that it takes the one kind of force, releases it like a release valve, it lets it out, and the other force gets trapped between the ping pong paddles. And that's the important part, to understand the difference between high pressure and low pressure. Yeah, that's good. Where do you live, sir? How is that relevant? Just, hello, sir. Hello. Where do you live, sir? What's the matter? Is that what you ask all the physicists, is where they live? If you met, if you saw Albert Einstein on the internet, the first question you have to ask him is, where do you live? Critically important. I don't think it is. But anyway, all right, so what was I going to do? The directional thing. Okay, so I think I've given you enough to understand that. So when a conductor becomes magnetic, it just means that each atom that's doing the pressurizing, that is, each atom that's now being increased in its pressure, okay, which is going to distort it, misshape it, and jiggle it, however you want to look at it. It's going to jiggle it, which you could look at jiggling this way or this way as a kind of shape problem. You could. And that's what's creating its lopsidedness. You could look at it that way. But anyway, the point is whether you think about it as a misshaping or a direction of vibration, the point is an increase in pressure. And basically in a conductor, how much electricity is moving, how much current, is just deciding how many atoms are involved in the process of exchanging pressure. So the more atoms exchanging pressure, the more magnetism. So the more you've magnetized. So when the pressure travels through, it magnetizes the atoms, the individual atoms that the pressure is moving through. And it's only magnetic while it's in this increased pressure, decreased pressure cycle. So only while it's transferring pressure is it magnetic. So it can be transferring from high to low or low to high, but it has to be transferring for it to be stretched. If it's not transferring pressure, if there's not a differential in pressure, it won't be stretched. It won't be vibrating in a different way, and therefore won't be causing magnetism. So the more energy you put in, the more atoms you stretch. Therefore, the more little magnets you make. Therefore, the more magnetic the whole thing becomes. Now, I did mention the curious fact that if you take two conductors that have current going through them in the same direction, okay, and so they're two conductors lengthwise this way, okay, and I'm just showing you the picture of them this way. There's this odd scenario where they're attracted to each other, where you would think they'd be repelling each other because they're enduring the same thing, they're doing the same thing, they're pressurizing the same way. Well, the trick to that is sort of like the Casimir effect, which is when charge decides which plate's going to be positive and which one's going to go negative. The thing they're probably doing is the atoms on the surface are just rotating one way or rotating the other way. So one rotates one way a little bit. You just sort of have to understand that there'll probably be lines of pressure, and that all it really has to do is have the lines out of phase, and then this one will be lining up with the red here, and this will be the brown here. So if these things were scattered here, you could sort of understand if there were spiked wheels, what the two will do is it will have the spokes line up with the empty spot on the other one. So this wheel will line up with this one's anti-spoke, and just naturally because of the repulsion. See, they'll be repelled here. So if they stay this way, they just repel. But if they move in the opposite direction a little bit, then this one will now be hitting proton on proton, blah 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 blah, and you'll create the opposite effect of the repulsion you would add here. You'll have attraction here, and so they're just basically lining up to the natural position. One tilts one way, one tilts the other way, and now they're lining up so they can be attractive. So it's just for that circumstance that it happens. If I made these into coils, the magnets would repel the way they should, because there's no way for the coils to do that. The coils can't, make a little tiny change in their position and, meet the other thing's opening. So there's no way to mediate against the pressure. Always something. 800 number. Hello? Goodbye.
Hello. This is Verizon calling with a message for Anne.
What message could you possibly
have? An important message regarding a change in the status of your account.
Hey, there's no change.
Please log into Verizon.
Oh, God, I hate these cunts. You pay your bill and they're just I don't know how they can be this obnoxious and get away with it. How do they get away with being this rude? You owe us $47. Let's call you, but you owe us $47. No, you mustn't call me for $47. If I owe you $447, then you call me. Oh, God. You're just saying, why? Why do we allow this in our civilization? Anyway. So bad. Anyway, so where was I? All right, so the distinction between magnetism and electricity, just understand. The electricity doesn't make the force of magnetism. It makes magnets. It magnetizes the atoms in the conductor and creates a magnet out of the density of the conductor. And that's why, if you roll a bunch of wires around, you're increasing the density of the wire, therefore more and more stuff to get magnetized. And then if you put a steel rod inside of a bunch of coils, obviously you have even more material you can magnetize, and therefore increase the utility of your electricity, in the sense that you're putting something right next to the magnetic field of the conductor, therefore it transfers completely into the conductor, the metal, making the metal as magnetic as you can make it, because it's all stuck inside. So it's going to get very magnetic because all of the reflecting stuff is going to keep taking place. There's no way for the reflections to escape outside of the coil. So you have a lot of capacity to magnetize atoms, that is, pressurize them inside the piece of metal you put inside. So it just magnifies the magnet. So the magnet's already, by rearranging the atoms, you magnify, you increase the potential pressure of gravity. And then by, properly arranging the magnets, you can increase or magnetize the capacity of the magnetism to make magnetism. Right. Okay. And so the only other thing I wanted to just touch upon was the sort of the simplicity of the rules here, because they really are pretty simple. All right. So the idea is you have the electron and the proton. So, I mean, I have done these drawings before, but I just want to illustrate what's taking place. So there's two forces in the field of gravity, the red force and the brown force. Okay, the electron force, the proton force. They're identical in all respects except of one property, which is electron force recognizes the difference and proton force recognizes the difference. They know the difference between them. And so brown force will always reflect off of an electron and just move the electron a little bit. Red force will do the same thing to a proton. Essentially, it will just exchange energy. It will give away an arrow reflecting, and it will retain a bit of momentum in the direction it's going. Now, when brown force hits a proton, what it's essentially going to do is make a field transfer. That is, this arrow will go out perpendicularly. It can be any one of these 4 subdimensions. So it can come out any one of the 2 perpendicular dimensions. But let's just say, for the sake of argument, it comes out this way. And what it's essentially done is it's made a transfer with a brown bit going this way. All right, so a brown bit came in, intersected with this brown bit. One of them will come out this way, and this one transfers. Oh, sorry. Yeah, so it doesn't transfer energy. It just transfers direction. So I drew this the wrong color. It's going to interact with. See, it's really important that you get this right. Okay, this. So it's going to absorb a red bit from the environment and turn it into a red bit going out perpendicularly. All right, that's the way it works. So it's going to take a red bit from the environment that was going to reflect. So this one won't reflect, and instead it will leave perpendicularly, and it absorbed. Yeah, and this is going to go in perpendicularly and leave perpendicularly. So this route will happen for the brown bit, for the electron bit, and this route will happen for the red bit. And that will be the exchange. And it won't involve any exchanges with the inside of the proton. It's just going to exchange forces, not anything else. All right, so that's a better explanation. So it's a slight variation from the simple idea that the brown force reflects and the red force detours. Well, the red force detours, but it does so by consuming, something going brown going this way. So again, so it's a little more complicated. All right, yeah, well, that part still probably needs an ounce of work. So anyway, but the important part is I think this explanation of charge, that is static charges and all that kind of stuff, which is basically just the pressure of the electrons. And for some materials, it'll just be on the surface because those are the only electrons that can be pressurized, because the insulator doesn't transfer pressure, doesn't transmit it well at all. The electrons are in such a position where they can't jiggle each other easily. in the different atoms, and that it has to travel through a medium. And if it doesn't, let's say you had empty space instead of this air medium to make these ions and to create this pathway, then what you're going to have to do is break little pieces off of this, atom, and throw them into the atmosphere to transfer the pressure. So you create so much pressure in one. That's why they use high voltage in like fluorescent lamps and other stuff. Is you're basically eroding the cathode to move this stuff to the anode in some respects. And certainly in plasma circumstances where people make a plasma, that plasma is made of the actual matter being torn off and the matter being pushed into the space and that turning into a medium for the transfer. Let's see, I don't know whether I need to answer this one. Well, I think that's working. Way overpaid cops looking for more money. It's just insane world. Just insane that they're allowed to do that. Unsolicited bullshit. Why? On top of the fact that they're way overpaid. Stuff that just shouldn't exist. No excuse for it. So anyway, so I've explained that in the relationship. So you could have a magnet that's both being a magnet and you're using it as an electric device. That is, you're running current across it too. And so you can create all kinds of double circumstances. But, well, anyway, I think I've basically explained this. So this is like, whatever, 85, 90% complete in terms of recognizing the difference between charge, magnetism, and the flow, the exchange of pressure. There is no flow of electricity. There's a exchange of the little bit pressure ping pong ball. So this one has ping pong balls and it transfers the pressure, just transfers the pressure. These are this far apart. These are this far apart. This one transfers pressure by moving and equalizes the pressure. And they're just transferring pressure, which is energy. Okay, so I'll leave that. Okay, so we'll see if we have any useful comments. Doesn't look like much is going to happen, but we'll waste a couple of seconds waiting to see if anybody has anything rational to say. I mean, this theory is getting so complete. I just don't know how anyone can deny it anymore. This can't be an accident. Can't be an accident that this fits this so well, that this is explaining it so well, so simply, and it covers the actual experimental observations. It explains why we see what we see. I just don't know how anybody reasonable can deny that the last 3 videos have just nailed it. It's nailed. And all I'm getting is crickets. Not the way the world's supposed to work again. Another thing that's broken. It's broken is that cop begging for money. They should have instead of a do not call list, I'm on it. Obviously it doesn't work. They should have a I'm as poor as fuck list, which just means just don't bother. I mean, I really don't have the money. So even if you had a great cause, I still can't give you any fucking money. So I guess that's enough. I guess. No point in just sitting around restating what I've already stated, so I won't bother restating it. I mean, I could go over it again just another way, but we'll save that for another time. So anyway, thank you for the non-participation. Yes, much appreciated. Let's see how many people were in here. 4. Oh, that's just fantastic. Jeez, brilliant. Ugh. Ugh, just disgustingly pitiful. You know, I just get writer and writer. Anyway, nothing to say. It's a mad, stupid, smelly, skanky foreskin world.